So far, we've talked about the broad categories of modeling problems as well as learning algorithms. There are a whole bunch of practical challenges that we also have to address whenever we're applying machine learning methods. And we'll talk about these over the course of the semester. But to give you a few hints here, one of the areas is that of the choices we make in the modeling process. So depending upon what type of problem that we're faced with, we have to make that choice of model and the type of and the choice of learning algorithm. And one of the concerns that we have to address is that of computational complexity, and this comes up both in the training process and in the querying process. By querying, what I mean is that we present a trained model with a new input, and we get a new prediction out of that. For some types of models, the training process can be very expensive, but the querying process can be very cheap, or vice versa. The training can be very inexpensive, or the querying can be very expensive. Another dimension is that of hyperparameters. So learning algorithm, its job is to select the parameters for the model. Hyperparameters are parameters for the learning algorithm itself. So an example of a hyperparameter might be how complex we're going to allow our model to be. We might also introduce something called a regularization parameter, which enforces certain kinds of smoothness constraints to our models. During the course of applying a learning algorithm to a problem, we might actually end up experimenting with different choices of hyperparameters. And so we'll talk about what the hyperparameters mean. We'll talk about how to at least make some good guesses, and then how to be very specific about how we choose our parameters in the end. We also have the challenge of how to select our data for the training process. Depending upon the kind of problem that we're faced with, data collection can be a very expensive process. In which case that will limit the amount of data that we have available to us. And different algorithms, different hyperparameter choices require different amounts of data. So we'll talk about how to figure out when we don't have enough data, and what we do when we have a very small amount of data for a given problem. One of the issues that relates to this is that of overfitting. And this is a scenario where we train our model. The model performs very well on the data that we've used to train with, but when we go to apply the model to new data that we haven't seen before, the performance is very poor. So let me give you an example of that. So here's an example of, say, so X is our input, and Y is our model output. And our training set is going to be a set of points here. And if I have a set of points that look something like this, we can imagine fitting a very nice linear model to that, and it doing a reasonable job of predicting these points. There's still some real error here and here, but we're actually capturing this point quite well, and this point down here quite well. So that's a very simple type of scenario. Imagine this kind of a scenario where I have, say, X and Y here, and my data points look more along these lines. So this is a situation where if I were to fit a linear model, I might end up with something along these lines. And that might capture the very general trends of the data, but it doesn't necessarily do a very good job. So what if I introduce a more complex model? So this is a hyperparameter choice I can make. Instead of using a linear model, I could use a quadratic model. And if I were to do that, I might end up with, say, a model that looks like this. And that does a reasonable job for many of these data points. But do I actually have to stop there? Why constrain myself to using a quadratic model? Why not use a third order or a fourth order or a 20th order model? And if I go to the extreme, I can do something like this. I can end up with a model that captures my training data really well, but might have this shape. So if I were to say query at this point here, so I have an input X here, that gives me a prediction of Y at that location. That's maybe not be such a bad scenario, but what if I provide a query right here? And what my model would do is make a prediction about Y at that location. And that's very different than what our quadratic choice would be, which would be this prediction right here. And depending upon the data that we actually have, this overfitting issue can be really extreme. We can make very huge errors if we get this wrong. Okay, so part of the semester, we'll spend some time talking about how do we detect these overfitting situations, and we'll also talk about how to mitigate these situations. Some of the algorithms that we'll work with will actually handle this situation automatically. In some cases, we have to also be very careful about the choices that we make for our training set. All right, another important topic that we'll cover over the course of the semester is that of making comparisons between models and algorithms. When we're actually going to field a model in the real world, we generally don't just train up one model and we're done. In practice, what we will do is make several choices about possible model forms and algorithms, and then ask an empirical question of which one works better in this scenario. But one of our challenges here is that performance is fundamentally so we're measuring performance of all our models, but in the end, this performance measure is inherently really a random variable. So there are statistical forces at work. When we go to train our model, we are selecting a certain set of data for the training set. So there's some randomness there. Some of the algorithms that we use also inherently have randomness built into them. And so if I present a model with one data set, I might get a learning algorithm with one data set. I might get one kind of model. If I present it with a slightly different data set, I might end up with a very different kind of model. And so we need to acknowledge this phenomena and actually take very careful steps when we're making choices about models and algorithms. And in particular, what we'll do in this semester is look at this from an empirical process. So we won't construct just one model, but we'll construct a whole bunch of models and ask whether or not there are consistencies in how they perform. This kind of issue also comes up when we're selecting hyperparameters. If I have one particular model and learning algorithm, and I want to make a choice about a value for a hyperparameter, we really have to ask that from an empirical perspective. So we'll practice this quite a bit over the course of the semester.